Chapter 14.1 Dependent and Independent Variables. An independent variable x explains the variation, which is a fancy word for change, in another variable, which is called the dependent variable y. This linear relationship between independent and dependent variable exists only in one direction and is as follows. Independent variable x determine dependent variable y. For example, in the used car market, the mileage of the car would be the independent variable and the price of the car would be the dependent variable. As the miles of the car odometer increases, you would expect the price of the car to decrease. This linear relationship between the independent and dependent variable does not work in reverse. For example, changing the price of the car will not cause a change in the odometer mileage. Other examples of independent and dependent variable are shown in Table 14.1. For example, independent variable, the size of a television screen determines the selling price of the television. The number of visitors per day on a website determines the amount of sales per day from the website. The curb weight of a car determines the car gas mileage. Chapter 14.2 Correlation Analysis. As I mentioned in the start of this chapter, a correlation analysis allows us to measure both the strength and direction of the linear relationship between two variables by calculating the sample correlation coefficient, or R. We first introduced the sample correlation coefficient in Chapter 3 when we used the covariance of two variables for our calculation. In this section, we will demonstrate a different procedure to determine the correlation coefficient. However, the Chapter 3 method can be used in place of the correlation coefficient calculation shown in this section. After R is calculated, you will learn how to perform a hypothesis test to decide if the linear relationship between the two variables is strong enough to be considered statistically significant. Suppose we would like to investigate the linear relationship between the number of hours students study for a statistic exam and the grade they get for the exam. Table 14.2 shows sample data from 6 students who were randomly chosen. This data can also be found in the Excel file examgrade.xlsx. Since I envision having your attention at this moment, I'm hoping you agree the hour of study variable is considered the independent variable, or x, because we expect that it affects the change in the exam grade, which is considered to be the dependent variable, or y. Using the sample from the previous table, we can create ordered pair x and y values such as 3,86 and 6,95. Figure 14.2 shows the scatter plot for the 6 set of ordered pair. Our job in this chapter is to measure the linear relationship between these two variables in terms of both the direction and strength. The next step in this process is to construct Table 14.3, which will provide you with the values you need for future calculation. The third column in this table is the product of x and y. The fourth and fifth column are the square of x and I, respectively. Every calculation that will be performed in this chapter can be completed using the 5 summation value shown in table 14.3 along with the value for n, which represent the number of ordered pairs in the table. For example, n equal to 6. I call these values the SIG numbers summary of correlation and simple regression, or SNSCSR for short. I suggest writing them down and putting them somewhere, as we will be referring to them throughout the rest of this chapter. The sample correlation coefficient. We are now ready to calculate the sample correlation coefficient, or R, for our exam grade example using equation 14.1. We know from experience that many of the students get that glassy-eyed or head-like look when they first saw this equation, but there is no need to panic. Pull out your handy-dandy SNSCSR values and simply plug them in very carefully. So R will be equal to 0.828. What exactly does the R value mean? As I mentioned earlier, the correlation coefficient R provides us with both the strength and direction of the linear relationship between an independent variable and a dependent variable. The value of R ranges from -1 to 1. When R is positive, the linear relationship between x and I and y is positive. This means that as the value of x increases, the value of y tends to increase. By contrast, when R is negative, the linear relationship between x and I is negative. So, as the value of x increases, the value of y tends to decrease. The strength of the linear relationship between x and y is measured by how close the sample correlation coefficient is to +1 or -1. Figure 14.3 illustrates the strength of various correlation coefficients. Graph A shows that there is a perfect positive correlation between x and y when r equal to +1. We see that the value of y increases at a steady rate as the value of x increases. Graph B shows a perfect negative correlation between x and y when r equal to -1. This is just the opposite of graph A. The value of y decreases as a constant rate as the value of x increases. This type of perfect correlation shown in graph A and B is rarely seen in business setting. Graph C shows a weaker positive linear relationship between the variable. In this scenario, y tends to increase as x increases, but not necessarily at the steady rate we observe in graph A. This type of linear relationship might be observed between the variable advertising and sales. That is, there is a positive correlation between the amount an organization spends on advertising and the sales it makes. Graph D shows a negative linear relationship between the variable that is slightly weaker than graph C because the correlation coefficient is closer to 0. Also, you can observe more scatter in the data when you compare this with graph C. In this scenario, y tend to decrease as x increases, but not necessarily at the steady rate we observe in graph B. Conceivably, this type of linear relationship describes the pattern that variables such as price and demand for many consumer products tend to follow. In other words, when the price of a product rises, people want, people want to buy less of it. Finally, graph E shows the case where r equal to 0, which means there is no linear relationship between x and y. As x increases, there appear to be no particular pattern for the values of y. Because r is equal to 0.828 in our example, we have discovered a very strong positive linear relationship between hours of study and exam grade. Those students who studied more tend to have better grades. Just what a teacher wants to hear. Using Excel to calculate the sample correlation coefficient. You can use the correl function in Excel to calculate the sample correlation coefficient. It has the following characteristic. Correl inside parentheses array1, comma have grade from 6 students, there are 6 minus 2 equal to 4 degrees of freedom for our example. Using alpha equal to 0.505 for a one-tailed test, the critical t-score is found to be T alpha equal to 2.132. We can also obtain our critical t-score for a one-tailed test using Excel t.inv function, which was introduced in Chapter 9. We need the absolute value for this function result because it returns the left tail area associated with alpha. For our exam grade, our critical t-score is t.inv inside parentheses 0.05, 4 is equal to 2.132. Because t equal to 2.9953 is to the right of T alpha equal to 0.132, we reject the null hypothesis and conclude that the population correlation coefficient is greater than 0. Figure 14.5 illustrates the result. We can now conclude that there appears to be a linear relationship between the hours that the population of students studies and their exam score. We can determine the p-value for this one-tailed or upper hypothesis test by using Excel t.dist.rt function, which was introduced in Chapter 9. P-value equal to t.dist.rt inside parentheses 2.953, 4 is equal to 0.0209. Because this value is less than alpha equal to 0.05, we can reject the null hypothesis. In the last example, we set up a one-tailed hypothesis test to determine if the population correlation coefficient was greater than 0. We can also conduct a two-tailed test to determine if the population correlation coefficient is not equal to 0. Thank you.